Hi and welcome to this tutorial on ionization energies. In the previous tutorial, we learnt about how to explain the trends in atomic radius, electrical conductivity, ionization energies and melting points as we moved along period 3 in terms of their structure and bonding. In this tutorial, we are having a look at ionization energies, of course, factors that affect them, successive ionization energies, and also trends and how to explain trends. When the S block elements form positive ions, the ions formed will have the same electron configuration as the inert or noble gases in group 8. So for example, if we had potassium, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, because we fill the 4s before the 3d. Now if we take that electron away, we're going to remove it from the 4s and we're going to end up with 1s2, 2s2, 2p6, 3s2, 3p6. And this is the same as the configuration of argon. So when we've got the P block elements, they're going to form negative ions, and those negative ions also have the same electron configuration as a noble gas. So if we had nitrogen, it'll be 1s2, 2s2, 2p3, whereas a nitrogen 3 plus ion that it would form is going to be 1s2, 2s2, 2p6, which is the same as one of our noble gases. So we know that our S block is going to form positive ions and P block is going to form negative ions. And here we've got an example of a specification point. Ionization. So it is the process by which an electron is removed from an atom or a molecule. And the process itself is endothermic. So energy is required to break those forces of attraction between the outermost electron and the positive nucleus. We've got to put energy into the system. And we know in terms of this diagram that electrons are going to move in shells around the central nucleus, and the different shells represent specific energy levels. And here we've got an electron being removed and ionization has been complete. There's our electron that we removed and we've been left with an ion. So our first ionization energy is the energy required, and this is often a definition, the energy required to move one electron from each atom of an element in 1 mole of gaseous atoms to form 1 mole of gaseous ions as a +1 charge. So you will see that definition written down a lot in textbooks. You need to learn it. It's a little bit of a mouthful, but it does make total sense. So gaseous, that's why when I'm writing this out, we're going to have my compounds or my elements in their gaseous form. So there's a generic example of what ionization is going to look like if you're asked to write out the equation. And here's a diagram of what's happening. There's the electron being lost and we're leaving ourselves with a 1+ ion and that electron. The second ionization energy is the energy we needed to remove 1 electron from each ion of an element in 1 mole of gaseous 1+ ions to form 1 mole of gaseous 2+ ions. Again, very important definition. So we're going from 1+ to 2+, the second ionization energy. Some students will say the second ionization energy is the energy required to remove 2 electrons to leave a 2+. It's not. It's the energy required to remove 1 electron from a 1+, 1 mole of 1+, to 1 mole of 2+. So here's our example here. We've got a 1+, we're removing the next electron, that's leaving us with a 2+ ion and the electron. So if we write that out, we would start with a 1+ charge, and we're going to end up with a 2+ and another electron. And successive ionization energies, the energy each time you remove an electron. So you remove one and then the next and then the next and then the next and the next. So a graph for a particular element of successive ionization energies is typically drawn. And the equation that we could write for it would look something like this. We're going to end up with X N gaseous plus my electron. Remember, you need to use the gaseous state symbol. So in brackets, G. So gaseous atoms are used when ionization energies are recorded. So as I said before, the first ionization energy involves removing one electron from each atom. So we're going to remove one from this one from this one, etc., etc. So you're removing 1 mole of electrons in total from 1 mole of atoms. In the definition, you have to say 1 mole of atoms rather than an atom, because the examiner might think that you've got 1 atom and you're going to remove Avogadro's number amount. So 6.02 times 10 to the 23 electrons from that 1 atom. Obviously, that's ridiculous and impossible. So you need to say you're removing 1 mole of electrons from 1 mole of atoms. And it's implied that you're going to take 1 from each atom. And a reminder from a couple of tutorials ago, a period is the horizontal row in which all the elements have the same number of electron shells. So there are my periods. So I've got 1 to 7 on my left, and then we've got our groups. So they're the vertical columns where all the elements have the same number of outermost electrons. So here are my groups at the top. We might refer to something called the shielding effect. So that is the repulsion between the inner electrons and the outer ones, and it reduces the pull of the electrons into the nucleus. Okay, so it reduces the attraction from the nucleus to the outermost electrons. As you can imagine, they're shielding that effect. So they're going to have to go through all this shielding in order to attract the outermost electrons there. So the more shielding we have, the less those outermost electrons are attracted to the nucleus, the easier they are to remove. And then we might refer to the effective nuclear charge. So that's just a measure of how positive the nucleus is. So if you've got 18 protons in the nucleus, it's going to be a lot more positive. It's going to have a much stronger positive charge than if you had 10 protons in the nucleus. And we then end up with something called the net charge experienced by the outermost electrons. So the effective nuclear charge is that net positive charge experienced by them. So we need to consider some factors here. We need to consider repulsion from the shielding electrons. How many shields do we have? And the attraction from the positive nucleus. So how positive is that nucleus? So the size of the ionization energy is determined by the strength of the attraction from the outermost electron to that positive central nucleus. So the stronger the attraction between those two things, the harder it is to remove that outermost electron. So the things that are going to affect that is the atomic radius, the nuclear charge, and how many inner shells there are, or shielding. So the higher the atomic, or the larger the atomic radius, the outermost electrons are further away from the nucleus, so the attractive pull is obviously going to be reduced. So it's going to be easier to remove that outermost electron. So you can see that this distance between the nucleus and the outermost electrons is much smaller than this distance. This is a greater distance. So the attractive pull here is going to be less than it is here. Then we have our nuclear charge. So of course 18 is a higher number than 10. We've got a greater number of protons. So the outer electrons are further from the nucleus, and hence the attractive pull is going to be lower. That's part of my atomic radius consideration. But here I've actually got a greater charge. Okay, so the electrons being attracted by 18 protons is going to make it pretty hard for it to actually be removed compared to 10. So you can see in this image, I've got two factors at play here. Although this has got 10 protons, it has got less of a radius. So it's a bit of a way up between the two. But I've got a greater positive charge, but I've got more shielding. So you can see, although I've got a greater charge with 18 electrons in the center compared to 10, although I've got a greater attraction, I've actually got 2 shells worth of shielding, 2 inner shells, and they're repelling those outermost electrons. Okay, so that's actually going to make it slightly easier. And so this is considering our shielding, and this has only got 1 shield or 1 shell underneath in terms of the inner shells. So we can compare our 2 noble gases here, neon and argon. So in neon, we've got a smaller atomic radius. So smaller atomic radius and a lower nuclear charge. Whereas in argon, we've got a greater radius, a greater charge, which has got an impact, but we've got more inner shells or more shielding. Now, really, I would say shielding is a key term, so we should really be using that phrase. So which one's got the higher first ionization energy? There's a few things at play here. So neon has got the higher ionization energy, and argon's got the lower ionization energy. Okay, so neon has got more shielding, so more inner shells, and a greater radius, which is going to make it easier for me to remove that outermost electron compared to neon. What about comparing these two? So I've got zinc and sodium. So zinc's got a higher atomic radius. You can see it's a bigger molecule, and it's got more inner shells than sodium. So it's going to have a lower ionization energy. It's going to be easier to remove that outermost electron because the attraction between the positive nucleus and the outermost electrons is less. Okay, so with our sodium, we've got a smaller radius, and so it's going to be easier. So that distance and the shielding overrides the nuclear charge. So the consideration of nuclear charge is overridden by shielding and radius considerations. So this one's got a lower and this one's got a higher first ionization energy. So students do often get confused by nuclear charge and may only consider that. They would say, oh, well, zinc's got a higher nuclear charge, therefore it's got a greater attraction, it's going to be harder to remove the outer electron, so it must have a higher ionization energy, which is incorrect. You need to consider the fact that the distance and the shielding outweigh the consideration of the nuclear charge, which leads to zinc actually finding it a lot easier to get rid of that outermost electron and therefore has a lower first ionization energy. When we consider successive ionization energies, we're considering the fact that we're not just removing one, we're then removing another, and then another, and then another electron. So each ion that is going to form is going to become increasingly positive as I remove more and more electrons. So I'm looking at the same element now. So I've just got an element, and I'm going to remove one electron, and then I'm going to remove another, and each successive ionization energy will be slightly different to the next. So the successive ionization energies increase with each shell. So as you remove the next electron, it gets harder and harder and harder to remove as we bump down in the shells. Because each time an electron is removed, even if you haven't broken into the next lower shell, the ionization energy is still going to increase because we've got a positive charge, which is now acting on less electrons. So it's going to be even stronger, pulling the remaining electrons into the center. So here, we're looking at the first ionization energy, and then we're looking at the second ionization energy, and then we're looking at the third. So we're looking at the successive ionization energies of argon. Okay, and as we move along, it's going to get harder and harder to remove each electron because the positive charge of the center is increased, so it's exerting that force over less electrons. So that force is going to be stronger. So it's going to be even stronger, and then by the time we get to here, it's going to be really strong. It's going to become harder and harder to remove it. If we want to understand successive ionization energies, we need to understand shell structure. So successive ionization energies increase between the shells as we move down the shells. So each time a new shell is broken and we go down to the next shell below, we're going to see a significant rise in the ionization energy. And you can spot that on a graph. But like I said before, even if you haven't broken into a new shell, you're still going to see an increase in the successive ionization energy because we're removing an electron from an increasingly positive ion. And remember, ionization energy is defined from removing an electron and moving it an infinite distance away. So when we remove that electron, we're just acting as though it's not going to have any impact on that remaining ion. The reason why we have to explicitly state that is because, of course, if you just removed an electron, it would just be attracted back to the positive ion. So ionization energy, we're acting as though we're removing that electron and we're moving it infinitely away. So it's definitely not, that is not going to happen. When we remove the second electron, it's attracted back more. Okay, so it's going to be even harder to fully remove it from the atom, and it's really going to be being pulled back. Hence, it requires more energy. So that attraction, pulling that electron back towards that atom or that ion, the stronger the attraction, the more energy is obviously going to be required to overcome that force. Therefore, the greater the successive ionization energy. Of course, with the first ionization energy, you're going to remove it from the atom. and you're going to leave a 1+ ion, and there's going to be some attraction. And then with the second ionization energy, you've got a 1+ ion, and you're removing another electron, leaving a 2+, and that attraction is going to be even greater, and it's going to require more energy to overcome. So we've got a lovely graph here explaining the successive ionization energies of a particular element. So every time there's a sudden jump in ionization energy, we can tell that there's been a change in the number of shells. So the next shell below has been entered. And you can find out which group that element is in the periodic table by counting how many electrons are removed before you get the sudden first rise in ionization energy. So we've only removed 1 electron here before we've seen the big jump. Therefore, this must be a group 1 element. So this electron must be in the outermost shell. Once that's removed, we've then bumped down to the one below, and so we see this big increase. Now, be careful with the terminology. I've just said a big jump. We should say a big increase, because a jump can mean above, up, or down. So when you're writing an explanation, you should be saying there is a significant increase in the ionization energy between the first and the second electron being removed, which means that this element must be in group 1. So according to the graph, this must be sodium, this element. Okay, so the number of electrons in the third shell was 1, then we had 8, and then we had the final 2 remaining. So I could actually identify the element from that graph. So we've just looked at the trends in the successive ionization energies for an element, but we can also look at the trends in the first ionization energies moving across a period or down a group. So this is where we're comparing different elements. So remember, the first ionization energy is the energy required to remove 1 electron from each atom of an element in 1 mole of gaseous atoms to form 1 mole of gaseous ions with a 1+ charge. So just a reminder, we've got X as gaseous, we're going to get X+, and that's going to be gaseous, and then E-. So remember that our first ionization energies are going to decrease as we move down a group in the periodic table. And this is due to 2 factors. We've got atomic radius, and we've got shielding effects. So the atomic radius is going to increase as you go down the group. So the atom is going to get larger and larger as we add more shells. And this is going to decrease the attraction between the positive nucleus and the outermost electron, making it easier to remove. So it's going to decrease the ionization energy. Also, as we move down, the shielding is increasing. We're adding shells. So that's going to decrease the ionization energy as well for very similar reasons. Although as we move down, we do increase the nuclear charge, this is offset by these 2 things. Okay, these have a bigger impact. So the nuclear charge we can add at the bottom, obviously that does increase, but it is overridden by the other 2. So as I said, atomic radius and shielding, nuclear charge does increase, but we need to focus on these as the main reasoning. And again, in an exam question, if it asks you to explain why the ionization increases down the group, you need to mention the fact that the atomic radius increases and the shielding increases too, and that the fact that overrides the fact that you've got an increase in the nuclear charge. So don't mention the first 2 factors only. You should also talk about nuclear charge and refer to it as being overridden. Also pick on specific elements. For example, if they ask about group 1, please actually talk about lithium to sodium, for example. Don't just talk vaguely, pick out specifics. Then you're actually able to quote an increase in the number of electrons. You can actually give numbers. So the electrons in lithium, there's 1, etc., etc. So we talked about how first ionization energy changes down the group. Now, what about a period? So as we move across the period, we're also going to get an increase in ionization energies. And this is due to 2 things. So we've got nuclear charge. Now, this is where it does matter. So nuclear charge, and we've got atomic radius. Of course, shielding doesn't change as we move across a period. So the nuclear charge is going to increase as we move along. We're going to add a proton each time we move on to the next element in the period. So the number of protons in the nucleus is increasing. And so the attraction between the outermost electron and the positive nucleus is going to be affected by that. The atomic radius is going to decrease slightly as you move across the period. Okay, it's a really subtle decrease because the nuclear charge is increasing and it's going to pull, there's no change in shielding, so it's going to pull those remaining electrons in more and more and more and just create that subtle decrease. So there's no change in the shielding across the period. So all electrons are within the same shell. So therefore, the attraction between the outermost and the positive nucleus is going to increase as you move across the period. It's going to require more energy to overcome that attraction and remove that outermost electron. So as I said, these are the main things we're looking at: nuclear charge and atomic radius. Shielding doesn't change, okay? But you should still talk about it in an exam response. So make sure you mention all 3 of those factors. So here we've got a graph, and we're not comparing successive now. We're looking at different elements, so lithium through to neon. And we're looking at the first ionization energy, so the trend. So as we move along, the nuclear charge is increasing, but the shielding effect stays constant. So effectively, the nuclear charge increases, and that's the main thing that's happening. So we're seeing a general increase as we move along, but every now and again, we're going to get a dip. So there's a couple of exceptions. So there's a drop between group 2 and 3, and there's a drop between 5 and 6, and you need to be able to explain why we have those drops. So we saw a drop there between beryllium and boron. So we'd expect the first ionization energy of beryllium to be higher than that of boron due to the increased nuclear charge and decreased atomic radius. Okay, that's what we'd expect. So increased nuclear charge and decreased atomic radius. So that's interesting, but we don't actually get that. So boron's outermost electron is in the 2p subshell. You can see this here, rather than the 2s subshell. So the 2p subshell is at a higher energy level, and therefore it's found further away from the nucleus. And it's therefore also going to experience a little bit of shielding from the inner electrons, okay, from the inner s's. So these 2 factors are going to override the effect of the increase in the nuclear charge. And this leads to a lower first ionization energy for boron than it does for beryllium. So the fact it's in the 2p, it means it's slightly further out and slightly more shielding. So it's actually easier to remove this 2p than it is to remove one from the 2s. So therefore, I've just explained the drop between groups 2 and 3 provides evidence for electron subshells. So it changes from the usual pattern of ionization energies. So it proves the difference between the S subshell and the P. We also saw a drop in the ionization energy from group 5 to group 6. So that didn't follow the pattern either. So on this occasion, the outermost electrons are in the same subshell for both the elements. They're both in the P, and there's very little difference in the atomic radius or shielding. So let's look at nitrogen and oxygen in more detail. So the 2p subshell, we know it's got 3 orbitals. And in nitrogen, we've got 1 electron in each of them. And remember, when we do electron configuration, they don't pair up. Okay, so 1 goes in. We think about the guests in the bedrooms. We go to the 3rd floor. There are 3 bedrooms available. We've got 3 guests. Each one would rather have their own room before they pair up. So each of these electrons is going into their own room. When we look at oxygen, we start to see the doubling up. So that's nitrogen and that's oxygen. So we're going to see the first 3 are filled, but then the 4th one is going to have to start to pair up. Okay, and you can see this more clearly in the diagram here. So this is nitrogen, and we've got our 2p's. No electron-electron repulsion going on here. Whereas with oxygen, we've got some repulsion going on. There's more repulsion between a pair of electrons within an orbital. Okay, so electrons in shared orbitals are easier to remove. So it's going to be easier to remove this electron, for example. It's going to want to leave. So less energy required, and therefore finally that means lower first ionization energy.